everyone, welcome to TRON Core Devs Meeting 5. On today's agenda, first we will see if there is some java-tron latest updates. Then we talk about SPV proof support, the application of Merkle Tree in SPV, how SPV verifies transactions on the chain, and the application of SPV. Okay. Okay, who else has some questions for Bill?
Just a quick question. If a SR misses the turn, does this process improve it by any chance? Because if a SR misses their turn, it's 3 seconds lost, and then it goes to the next SR. Does this speed that up or help improve that?
It's okay. Every SR have assigned to one slot producing SR, right?
Yeah.
And then once the SR finish producing block, they should be waiting for next cycle. So they have no ways to get speed up for this process because every SR have his own slot. They can have no choice. Just wait until he gets time is counted on his slot. Then he will start produce. And then if you guys ask me some optimization about this, I guess I need to talking to other developers for something. Like if SR, like what you say, if some SR goes down, and then this log is empty, right? We do not want to wasting time. We probably want to other SR produce a block on this node, but there's a lot of complicated stuff will happen if we do that. So we still need to talking about with our developer to have a better solution for this. It does make sense?
Yes, that's fine. That's fine.
Yeah. Okay. Yeah. Thank you.
And from what we can see from screen you share, you said it before. SR list should be supposed to be an array or list, but why there is a bias? Could you please explain a little bit why you use bias and how you use this bias to locate the SRs or the get index of different SRs? Thank you.
Well, the reason why we use bias is that is save memory and also hiding SR identity. Once verify receive those SRs, they can decode it. And then currently we just implement a stream bit, which means you just convert a list into stream bit. There are a lot of library we can do it. So like Java, C++, anyway, pick up, just convert into bits. Yeah.
Hello, I have a question.
Sure.
What if the SR signature was signed by less than 2/3 SRs? Is it a still void signature?
Yeah, that is very good question. I'm not sure currently how we handle it. But as I talking before, before I come up with my idea, my original idea was that we can have some hash algorithm, like there are totally 16 XR, we can use 2 bit to do hash, and then we have a lot of hash value until we do 16 hash or 70 hash value, and if the eventually hash value is 0, then we can do validation. But this seems to be complicated. And then as soon as I figured out, I talking to my coworker, they told me we have easy way to do it. We have one easy way to do it. Just like we just do not put any value on SR signature if they're less than second, third SR, just like empty stuff or non-value, and then that is the way how we handle that. And then your question is like, absolutely, that's not invalidate signature if they're less than second, third SR, fine, yeah.
Yeah, I think the second solution would be a better choice, as it saves memory, no need to store a list or array.
Yeah, that's smart. Yeah, which reminded me the new feature of Program 3, which remove the field if there no data or none. It's like you get this message, you find out no any field as our signature. It can be empty, it can be none, which means it's less than second, third signed as block. So it's validated. So just we have to get it. It's so direct. Yeah.
What kind of information are stored in the current SR list and the next SR list? Just SR identity or something else? How did you use those yet? Can you give an example?
Sure. I would like to say it's just SR adjust. I talking to my coworker before. We have a lot of choice, but as soon as we figure it out, SR list is the most efficient one. Like we can have two SR, right? A and B with address of aux1, aux2. So the next SR list would the string like can bind together aux1 and aux2, just can calculate the two string into one string. Like eventually you will get a string like aux1, aux2, aux2, something like that, and then you convert into bit. So that is how we do it. Yeah.
Okay.
Or you can yeah.
Okay, thanks. As mentioned before, the verified will check the date to determine the new SR list is legal or not. How? Like use SR signature? What's the relationship between SR signature and the next SR list?
Well, we just use SR signature to validate next list. Yeah, seems like it's very cool how we do that. I talked a little bit before, like current SR signature would be generated by the previous SR list with modern second, third SR sign. So we'll design an algorithm like like what would I say? They sign like a signature algorithm. They can when they're trying to sign the block, they will with their SR adjust. And then once you have get the signature, you can decode it, get SR adjust. So you can take this value SR signature. You can get all the possible adjust where they sign the block. And then once you get that, you are comparing to the next SR list, and you comparing the adjust is equal or not. Once you get all the possible adjust, and then you can validate SR list. But still, they have some thing we need to discussing further because some like Prepotential or AZ asked me like something about the maintenance, what happening on the maintenance patrol, and what happening on the new block, and for the SR list, is that the same or not? So we also need to figure it out on this question. I will give you more good answers as soon as I figure it out with my team, with my coworkers. Yeah.
Okay, thanks.
Okay, my question is how SR and verifiers talk to each other. Is there any different protocols for that?
Well, basically, just TCP is enough. Everything is TCP, that is correct. But since we implement PBFT for mixed consensus algorithm, I would like to say we may use two-phased protocol to do PBFT. Since this protocol was also implemented in PBFT paper, we just do a little bit of change for the BPFT message. As you guys know, normally in PBFT, they including like TCP sequence number or replica ID, and then they use two phrases protocol to do consensus stuff. Like they have prepare, commit, and finally reply. They have like 4 stages. So the reason for that, for them maintain the 4 stages, is like they want to reach consensus in the distributed network, like they along the fourth torrent. So accepting this message, we we are trying to put a style list into the BDFT message so that we can we can qualify the block very easily. As we mentioned before, once we get to the list, we can qualify the block very list. We just take a look at the signature. We see fine, and then it's validated block. We do not need to like ask waiting for more than second, third style to sign and then agreeing. So it's so fast. We have it. Yeah. So if you guys want to know more detail about this, you just take a look at the PBFT. What is PBFT? Take to learn at the paper, and also take a look at the TICP, maybe other mixed consensus or math mixed consensus. They have a lot of detail how we do that for our TRON mixed consensus algorithm. So it's well better understanding for you guys to know. I do not have enough time to cover this. I'm done with my part.
Okay. Thank you, Bill. So maybe let me give you an introduction of the application of the Merkle Tree in SPV. Basically, Merkle Tree named after Ralph C. Merkle, who is a famous cryptographer. It's like a hash tree, which uses the hash function to connect with each node. The value of the leaf node in Merkle Tree is a data block hash, while the hash value of non-leaf node is a mixture of several other nodes' hash values. It's like we can hash two values into one non-leaf hash, which is also the root of those two. So might be sounds a little bit complicated, but I'll give some more details as long as any one of you would like to ask questions.
Hi, sir. What's the specials for Merkle Tree?
Okay. First of all, it's a tree. Like the majority of the trees, it has some common features like similar node structure, as well as log n for search time, log n for tree height, balance or recursive traverse, and etc. Well, secondly, only the value of the leaf nodes in the Merkle tree can be a data block hash value. That is to say, non-leaf nodes cannot, since those hash values came from different hashes of these leaf nodes. And thirdly, it saves memory. As you guys may have mentioned before, it doesn't need to store everything in the blocks. We just need a root hash, and then we can verify all the data along it. And lastly, like most trees, binary search trees, for example, we do the traverse starting from the root all the way to the leaf nodes. But in Merkle tree, we do it in an opposite way. As you think about the features of the hash value, it cannot be reverted. So in other words, we cannot get the original data from a hash value, which is to say, we cannot start from the root, since root hashes get from the subsidiary nodes hash values. So the traverse should start from the leaf all the way to the root.
Okay, there are so many advantages for Merkle tree. Can you explain why Merkle tree is good to use in SPV in blockchain comparing to other trees or other data structure?
Okay. Firstly, let's talk about the SPV, which is the simple payment verification, which is a kind of payment verification method in the blockchain payment system. It is convenient, fast, and memory efficient. It does not require to download whole blockchain data. It just keeps the block head. So it's said to be a lightweight data structure. Well, I guess I may share the tree diagram to you guys, which is easier to explain that. Okay. So inside the block head, we just need to store the root hash, and then all the transactions inside this block, since the Merkle tree provides the two features. First, it is highly efficient. Let's say to validate all the transactions, just compare the root hash of those transactions, see if they are equal, and then it's done. And secondly, it is highly secure. So, for example, if transaction C at the bottom changes, then it will lead to its hash N2 changes, and then N5, and also the root. So it is impossible to create a fake transaction within the SPV. And in addition, fast troubleshoot can be done by comparing the different hash values of nodes. So like the above example, from root to N5 to N2, all the value will change, and then we could locate the change of transaction C.
Okay. Hello, Matthew. What about the implementation of Merkle Tree?
Okay. Well, the initial goal of Merkle Tree is to handle Lamport one-time signature efficiently. Since every Lamport key can only be used for signing one message. But with the help of the Merkle Tree, signing one message would be equivalent to signing multiple transactions along the tree in one time, as you can see in the diagram. So which makes Merkle's signature scheme to be said as an efficient digital signature framework. And also in the P2P network, Merkle Tree is used to check whether the block receiving from nodes are damaged, replaced, or to ensure that the other nodes cannot be fraud or publishing a fake block. And as we may have mentioned before as well, most SPV implementation would store the head hash inside the Merkle Tree, so we may see if there are any data changes inside the leaf node, and it will recursively affect its parent node hash and finally the root hash as well. All right, if no more questions, then that's the end of my part.
Okay, so could you tell me the difference between SPV and normal transaction verify?
Okay, I will talk about this. And firstly, you should know the normal validation, the transaction validation is complicated. Okay, so as include multiple checking as the account balance and double spend problem. Well, usually these jobs are assigned to the nodes who are the entire blockchain. We call that full node. Yeah, this works are assigned to them. And comparing to this SPV is easy. Okay, as it doesn't have to know about anyone's account information. Well, the only thing it cares is checking whether a specific transaction does it truly exist in somewhere in the blockchain. Okay, so as you all know, of confirmed transaction is always the longest chain, which means it has been approved by the majority of blockchain nodes. Namely, it exists in the longest chain, or not since the post consensus proved the transaction by majority consensus. And if there's a fork, the longest chain is also kind of majority consensus. Well, that is to say, only a block header is needed for verifying payments by comparing the root hash of the block header with the predictor root hash. All right?
Yes.
So I have a question. Why use SPV?
Why use SPV? Basically, it's for convenience. In the Bitcoin world, general real systems have mining machine, and they do not have enough resources to run a full node. For now, you need about 200 gigabytes hard drive space to store the entire blockchain data, and a solid-state drive is preferred. For most users, what they need is only selling and buying, since they don't care about the verification process. Well, so a mining machine seems a bit redundant. Okay? SPV appears to solve this problem. SPV is lightweight, as it stores only block headers. A few megabytes space is required. From the block headers, we are able to know whether the transaction appears in the block, which can prove whether it has been verified.
Okay, could you introduce the process of SPV?
Sure. We can. Okay, so I will show you something. A moment, please. I'll show you something. Yeah. Can you see this?
Yeah.
So basically, first we're computing the transaction hash. Okay, and from a full node, getting the corresponding Merkle proof, and based on the Merkle path, doing that Merkle proof and finally get the Merkle root. Okay, and comparing local Merkle root with the calculated one, and finally you can judging if the transaction is legal from whether the result is equivalent to the local Merkle root. That's almost.
That's very clear. So how to get a correct block associated with the transaction, which needs to be verified?
Just give a transaction hash, okay? Well, we have database to store this. So simply query the database. You are able to get.
Okay, so just query from database. There must be like a table or something else to record this information, right?
Yes, exactly. Or transaction ID and block height. And also we do indexing for transaction ID because there are too many requests to getting block height.
What about the transaction that is not solidified?
You mean the verification process?
Yes, how to verify transaction that is not solidified?
Basically, first you can grab the Merkle path and the block height from a full node by using the transaction ID. Then, after you get a Merkle path and the block height, you're able to find the block header and, of course, the Merkle root. Okay. You can generate a new Merkle root by the transaction ID and the Merkle path and check if the new root is equivalent to the old one. And if they are consistent, means the transaction is in the blockchain. You may also check if the transaction is solidified. If it has received a number of SR commits, which is more than 2/3 of the SR number, yeah.
Okay. How to get the Merkle proof?
How to get the Merkle proof? Well, basically, Merkle proof is the Merkle path and block height obtained from a full node. Well, the Merkle path first obtains the block information through the transaction ID. Then the block contains transaction list, and the transaction Merkle root in the block head is generated through the transaction list. And, well, finally, by looking for the position of the transaction in the Merkle tree, the nodes that generated the Merkle root are continuously obtained from the bottom up. The list of these nodes is the Merkle path.
Okay, so once I get the Merkle proof, how to verify it?
You mean the verify the Merkle root proof? Okay. So, firstly, you get a Merkle path and block height, well, from the full node. And secondly, you just regenerate the Merkle root of the transaction by using the Merkle path and your transaction ID. And you can grab the corresponding block header again through the block height and compare whether the Merkle root you generated and the original one, if they are equivalent or not. So, and if so, the verification is successful.
Could you please tell me the pros and cons of SPV?
Pros and cons of SPV. For pros, basically, the saving storage, as I just said. For now, the block generating speed is 6 per hour, and each block head is fixed size as 80 bytes. So, just do a simplest calculation, you may find even your mobile phone is able to carry this data. And sure, it has some cons. An attacker can create a total identical transaction like the same input and output in the P2P network here.
Oh, thank you.
Okay. That's pretty much for me.
Okay, thanks, Thackeray. If no more question, I will move to my part. So I will introduce the application of SPV. As Matthew mentioned before, SPV is the short name of Simplified Payment Verification. Satoshi Nakamoto already introduced this conception in his paper. He mentioned that the payment can be verified without running a full node. What only need to do is saving the block headers. Regarding how to implement a lightweight wallet, so that depends on your purpose. So if the purpose is only about transaction verification, so integrated SPV is enough. Instead, SPV, if you still need to query account balances and establish new transactions, then all the transactions related to the user must be saved. We can get to the user's balance and other information from all these transactions. Do you have any question?
No. What are the advantages of Light Wallet?
First of all, it really saved storage space, and it could be easily running on a mobile phone because it didn't require huge resources. So everyone with wallet is decentralized.
Oh, okay.
Okay. Next topic, I will move to the cross-chain. It's kind of like the info sharing. So the cross-chain is the hottest direction of the blockchain. And the cross-chain can be implemented through centralized method or decentralized method. As we know, the centralized way is much easier to be implemented compared to the decentralized way. However, the blockchain advocates the decentralization. So based on this, TRON choose to use the decentralized way to implement the cross-chain. And SPV played a very important role in this decentralized implementation. Okay, so what kind of role does SPV plays in the cross-chain technology? Basically, SPV is used to ensure the security of the cross-chain technology. With SPV, we can easily verify the transactions, make sure they are confirmed and valid on the other chain before we use it in our chain. Okay, can you introduce some modern technologies which use cross-chain? So far, we have around 4 different cross-chain solutions. They are called, the first one, notary schemes. The second one is side chains or quad relays. The third one is hash locking. And the last one, distributed private key control. We will not go to all these details about these solutions. Please check from the internet if you are interested.
Is there any cross-chain project is based on SPV technology?
Yes, of course. Cosmos and Polkadot are the hottest cross-chain projects. They are all based on SPV. The common part of these 2 projects was that every chain will store the block head of the other chain. And they use SPV technology to verify whether the transactions are confirmed on the other chain. So generally speaking, in cross-chain technology, most interactions between 2 different chains are using SPV. The benefits of this design are obvious. As you know, a normal transaction verification requires large amounts of data storage. Considering that one chain needs to interact with several different chains at the same time, I think we think that it's not practical to store all accounts data. However, verifying a transaction through the SPV only needs to store the headers. The payment verification can be quickly performed. Okay, hello, Vincent. As you know, the security is very critical in blockchain technology. So how does SPV solve the problem of mutual trust between 2 different blockchains? Basically, I would say that this part is already covered in previous section, but I will give more info here. So first of all, it's very difficult to falsify transactions which already passed the SPV verification. Because the data is stored in the Merkle tree. With this tree structure, every non-leaf node is generated based on the hash value of its child. Means any change inside the tree will lead to root node change. It's very easy to prove that the data is hacked or crashed if you only change the data of the content of one node. Matthew already introduced this part previously. It's also very difficult to fake a non-existent transaction. So any change inside of the block, will lead to the block header change, and blocks are connected one after one. So basically, based on these facts, we can say that the transaction past SPV verification is credible. Okay, that is almost my part. Oh, okay. Thank you, Vincent. I think that's pretty much all we need to talk.
Hello. I just want to give more. Hello, Crypto Green is still there? Hello, Crypto Green ZA? Oh, guess no. I just want to give some a little bit of detail as we discussed before. Something's not clear. I just got something from my coworker, the guy who designed this DXCV. He told me the SR signature would be different for each block because the block was signed by different SR. It cannot be signed by the same SR every time. So the SR signature would be different every time. But it can be the same for the two blocks because if these two blocks was signed by the same SR, like they was by state 19 SR. They have all the 19 SR signed the two blocks at the same time or at a different interval. But the probability of this case is extremely low. Yeah.
Oh, I thought what you were getting the signature of the list, and of course every block the signature will be different, independent of the signature or not, because the data will change, so the hash will change and the signature will change too. But you can't get the public. You can extract the public key from the hash of the block, and if it's the same SCR, the public key will match. So if you have the list and sign the whole list, it should be the same for that cycle, the signature of the list. The blocks will change every time, the signature of the blocks. But you can extract the public key and check on the list.
You get it. Exactly. Yes.
Okay, is there anyone who wants to add something? I think we are running out of time. No? Okay. Our meeting, I think, will end here. Okay. Have a good day. See you guys.
Thanks, bye.
Thanks for joining.